Take a look. This is actually the introduction to the Nyquist plot, right? So I'll just use this for your understanding first, and then we go through the things that is required for a Nyquist plot. I mean, yeah, Napola locus lah, which is Nyquist plot. So if we can see that typically all about is phase and magnitude of the frequency. If you remember finding the phase and finding the magnitude. And this phase and magnitude all depends on the frequency if you remember the table. Okay, if you let me go through the table. So you hold on around. You can see I'm plotting my frequency, my magnitude, although I didn't write properly, and then the phase angle. Okay, and then when I plot, when I plug in certain frequency, I'll have certain values of magnitude and phase. And then with these values, and then I can plot my root locus, right? I mean, not my Nyquist plot, shit. Okay, and yeah. So there are a number of steps to sketch the polar locus. Okay, so first you have to determine the behavior of the magnitude and phase as omega tends to 0, and is determined by the number of pure integrators. So if you remember pure integrators, where are the integrators part? Hold on. So these are all the integrators, right? If you still remember, okay. 1 over S, this is the simple integrators, double integrator, triple integrator, quadruple integrator. And then as you can see, they are coming from these directions. And why are they coming from these directions? If you remember, they're actually due to the phase angle. If you remember, we proved that the poles and the zeros, phase angles of the poles and the zeros, we derive using the complex number. Okay. If you were to take a look. Okay, so if you remember, this is the portion over here that I'm talking about. Where we first start off with a simple leg, okay, 1 over s plus 1, and then I put in j omega, and then after that I just simply rearrange in terms of the conjugate, after which you can see that I have becomes a negative, and then this j omega, as you can see, so this is the real and this is the imaginary. And if you remember, this is the phase angle is determined by the tangent, where imaginary divided by real. So the imaginary sense is negative, so therefore it's negative. So the poles will contribute a negative, while the zeros will. So the poles will contribute a negative angle, the zeros will contribute a positive angle. Okay, please remember this. Okay, and then after which we talk about what do we talk about? Hold on. Determine the behavior of the magnitude and phase as omega goes to infinity. The phase is determined by the relative order of the system. What is the meaning of the relative order of the system? As you can see, okay, sorry. Why am I over here again? Shit, lagging, hold on. So this is actually the relative order that I'm talking about. So let me ask you a question if you are already pro already. So what will be this phase angle be? Okay. So if you think about, it's pretty easy, right? It's actually negative 180 degrees. Straightforward. Okay. You just need to memorize that how many orders are there. How many. Okay. So there's fourth order, as you can see there is 4 functions. And there is 2 functions over at the top. So there is 2 degree and there is 4 degrees. So therefore, as you can see, if you were to overall, this is m, this is n, right? So m minus n is equals to 2. So 2. So the poles is dominating, right? Because there is the pole in the denominator there is 2 degree. So therefore 2 times negative 90 degrees. So this is the relative order that he's talking about. Okay. So what if we have 1 over s squared? What will be the relative order now? Okay, it's simply minus 360 degrees. Okay, this will contribute 180 degrees for the zeros. This will contribute minus 360 degrees, and this will contribute minus 180 degrees. Right? Actually, this is 1 over s squared. Okay, so as you can see, if you cancel away, because 180 plus minus 180 is, so you have a minus 360 degrees over here. So this is the case, and then let's go back here. And this is actually what this is talking about. For auto system, j omega 0 as omega goes to infinity. So we are only talking about the from 0 to infinity, that's all. Okay. So we didn't talk about the negative negative sides. As you can see, I think this Nyquist plot is totally one case. Actually talking about when frequency is equals from 0, okay, 0 point something, from 0 to infinity, okay, as you increases, 0 to infinity. We're only talking about the real axis. I mean from 0 to infinity. We're not talking about from 0 to negative infinity. Right? If you were to look at this, we're talking about this portion over here only. If you talk about negative frequency, is not in our, because it's just refraction. So you can see it's from 0, okay, 0 to negative infinity. So we are not talking about this. We're only talking about this portion over here. And then determine the corner frequency of any leg lag. This one I think is the Bode plot. So but you make sure you know the delay. Okay, and the frequency and the point at which the locus crosses the negative real axis is important. So crosses the real axis is important. How is it cross the real axis, right? If you remember, this is the real and this is the imaginary, right? So if it crosses over the real axis, negative real axis, right? Make sure it does not cross over the negative one. Okay, so what he says is just simply a very general term. Okay, in which the frequency at the point at which the locus crosses the negative real axis is important. So at which it crosses this real axis is important, because you do not need to cross over negative 1, because all these are unstable. And then if you still remember our performance criteria, our phase angle has to be minimally 40 degrees, okay, away from the thing. So as you can see, these are all the zones that we want to keep up of. So if your locus is within this white color spaces, okay, you are safe. If you are inside this red color zone, or all the way, you are actually unstable. So this is actually what we actually do for the performance criteria part. Okay, so this clear away for this portions over here. What I want to give you a full understanding of what we have actually learned. So the second part of this summary is actually to summarize what you're gonna do when you're given any root locus transfer. If you are given any transfer function, make sure you know what to do. So if you are given a certain function, make sure it is open loop transfer function. It is not a characteristic equation. If it's a characteristic equation, you may need to know how to do. Let's say if you have a s squared plus 2s plus 1, right? This is a characteristic equation. In order to change to non-characteristic equation, okay, in order to change to that, you have to first divide it by s squared plus 2s plus 1. Okay, and then okay, my fault. The characteristic equation should be plus k. Okay, for example. Okay, the characteristic equation should be in this form. Okay, if you want to change to a open loop transfer function, what you need to do is actually divide the whole equation by s squared plus 2s plus 1. Also divided by everything by this one. Okay, what you'll get is actually plus k over plus 2s plus 1, which is 1 plus k s squared plus 2s plus 1. As you can see, this is actually 1 plus kgs, right? And since you know that k is just a multiplier, so you know that this is the open loop transfer function. Because the closest transfer function is actually open loop divided by 1 plus kg open loop. So once you get that, you know that the open loop is actually 1 over s squared plus 2s plus 1. From there, you can actually know how to solve for your other stuff. So make sure you know how to acquire the open loop transfer function, and then let us continue. So once you identify that it's actually an open loop transfer function, okay, the next thing you need to know is to switch s equals to j omega. Okay, as you can see, um, okay, I think you get what I mean, okay. So actually your transfer function, for example, right? What you need to do is reach s equals to j omega, right? Then you just sub in s equals to j omega, and you have this portion over here done. And then the next thing you need to do is actually what do I need to do? Okay, close this already lah. Okay, and then you can find your magnitude and phase angle, which is in this case what I've found earlier. Okay, this is your magnitude. You just need to use 1 square. So in this case, you want to find the magnitude for this thing, right? What you're gonna do is simply so let's say you have a transfer function over here. You change to s equals to j omega, which is this one, right? And then if you want to find the magnitude, okay, we're just simply taking only omega and 1. We just square them, okay? The j is just saying that it's in the imaginary axis, so you don't care. Okay, so therefore it's omega square plus 1 square. And then if you want to make things simple, okay, you can just factorize out the 2. So I'll have the 2 outside. So when factorizing, you're just simply saying that divided by 2, and then you're applying 2 outside. Okay, so I have 2 half j omega plus 1. Okay, and then in this case, because I want to find the magnitude, right? So it's 2. Since j is not a constant anymore, it's just saying that it's in the imaginary axis. You will have 1/4 omega square plus 1 square square root. Okay, so in this case, you can just straight away find your values. But nonetheless, you can also keep this thing. You can only do factorize. Sorry, but it is recommendable if you were to do that. I don't know why, but yeah, plus minus, you go and check it out. And if you want to find the phase angle, I already say if it's poles, okay, 1 over s plus 1, it is negative tangent, and then imaginary over real axis. If it's zeros, it is some s plus 1, and then it is positive tangent inverse, and then imaginary over real. So in this case, imaginary is omega, right? So it's omega over 1. Okay, omega. So in this case, if it's 1/4, okay, it will be 1/4 omega. Sorry, it will be half omega over 1, because you're not talking about this, okay? Because you're squaring already, but before that is 2 half omega plus 1, right? So make sure you know that this is your real and this is your imaginary. If you do that, this is actually the magnitude. So please be careful of that. So after which you know your magnitude and the phase angle, you also roughly understand the Nyquist using the integrator and lag concept. Okay, if you were to remember. So this is actually when you have multiplying, if you have no integrator, yeah, if this, so this is simply only one. Okay, let's show you. Okay, this is not I didn't say it properly. So this is simply 1 over s plus 1, which is a simple delay. Okay, so this picture is only saying if you introduce one integrator, what will you change, how will you change the graph, right? So if you have no integrator, you are at this portion. If you were to have 1 over s, okay, multiply into, that means if you have, okay, where is it? Hold on. Yeah, if you have 1 over s times 1 over s plus 1, okay, you will have this type of thing over here. So basically, the key trend that I want to show you, is this. If you still remember, if you still remember this classic way of representing things, okay, if I have a 1 over, if I have 1 over s plus 1, I have some root locus like that, right? If I introduce 1 over s, I'll actually flip this portion over here in 90 degrees. Okay, I'll be here, right? Okay, 1 over s. If I were to introduce another 1 over s, okay, I am actually tilting up again. And then if I were to introduce another 1 over s, I will actually go to here. And then I introduce another 1 over s, I will come to here. I'll go back to here, but the gain, the locus itself will change already at the shapes. If you have like 1 over s, okay, you have quadruple integrator, you're actually changing the whole shape lah, okay. I don't know what the shape, but it will not be like that, but rather than some other magnitude already. Okay, and therefore once you understand how the Nyquist plot will look like, okay, and also the trend that I've shown you, that where is it? So if it's minus 90 degrees, right, you're at the fourth quadrant. If you're minus 180 degrees, you're at the third quadrant. It comes in this manner. If you're minus 270 degrees, it comes in the second quadrant. Okay. If it's minus 360 degrees, okay, it comes in the it comes back to the first quadrant. Okay. So yeah, this is the case. So these are the trend you need to know. And once you, because how do you know this trend? Okay, from your face angle. If you were to take note of the, where is it? So from here you can actually roughly gauge how many angles are there. Okay, you have, so typically if you were to plot how do I say so this face, it depends on the relative angle lah. As I said earlier, if you have a number of poles, let's say s plus 1, and then s plus 2, s plus 3, right? So this contributes 90 degrees, and then this contributes minus 180 degrees. The summation of these two will have minus 90 degrees. So you can actually, from there, you can actually know where is the root locus coming from. Okay, actually minus 90 degrees is actually, this is over, it's actually yeah, never mind. Yeah, it's correct. It's that. Okay. So it's a little things you need to really go and take note of. I suggest you go and watch. And then sub in different frequency. Okay. So now you can actually sub in your different frequencies. 0. So firstly you have to sub in your 0 and your infinity. And then you plot it out. Slowly you can plot one by one. Okay, let's say you have this one, and then you plot maybe at 0, frequency equals to 0, and this is where frequency equals to infinity. So when you start to plot, you can actually plot, and you get this locus. What's good with plotting 0 and omega, I mean infinity first, is what, okay? If let's say you plot omega is equals to 0, it's infinity, it's somewhere over there. It's minus infinity lah. Okay. Shit, I'm lagging now. Okay, I just close this one first. It's minus infinity. And then you know that as omega goes to infinity, this is omega equals to 0, equals to infinity lah. The magnitude is infinity. And then this is where omega equals to infinity, when it comes back to this point. So you know that it comes from somewhere over here. So you can roughly gauge where the Nyquist plot can be plotted, and then you can know how to plot the thing. So this trend is very important. If you don't understand the trend, you are dead. Okay, you are simply like a kacwa. You are dead. Okay, so you just spread the data and then you just plot lah. Okay, so after which you can determine your stability along the root axis. If to determine the stability along the root axis, you make sure you know how to do it. Okay, this is you just watch this video on set up an equation for Nyquist. So you just watch this series of videos. Okay, intersection to Nyquist plot to real axis. Okay, there's two methods, imaginary and real. What the key things I want to let you know is trigo and complex rules. Okay, so what is the trigo and complex rule? Make sure you remember this one. So let's say you have a plus bj times a minus bj, so it's conjugate multiplication, right? So if it's odd number power, okay, let's say it's 1. So you have a square minus bj square, so it's minus. So if it's square, which is even number, you will have a plus. Okay, so the difference is only minus and plus. So this is the trend, and I may be wrong, but it should be the case. Okay, and then trigonometry, you need to know these two equation. If it's tangent inverse a plus tangent inverse b, you have to is a plus b divided by 1 minus ab. Similarly, not similarly but rather than comparatively, ABC is a plus b plus c minus abc divided by 1 minus ab, and then minus ac minus bc. It's like the probability rule lah, okay? So this is how it works. After which, why we want to determine the real axis? Because we want to find the lambda, right? The lambda is actually your values from the origin to this place, right? The smaller your lambda, the higher your gain margin. You want your gain margin and phase margin to be high. Okay, the higher the phase margin and gain margin, the more stable you are, right? So in other words, if you have a graph over here, okay, so if your lambda is very small, okay, compared to -1, you're further away from -1. And if your phase angle is actually this big, okay, if your phase angle is actually this big, you're very safe, right? You're very safe from -1. So this is what is trying to say lah. Okay, and then otherwise you can determine the stability for complex number using the phase margin, which is the phase margin talking about. So for the real axis, right, stability along real axis, which is this along this line, you can find lambda using just now the method, the complex and the trigo. If it's this one, you can actually use you can actually plot. Okay, you can actually plot using your protractor, okay, and ruler. So you just know the angle. What is it? Okay, simply it's just saying that, let's say if you have a root locus lah, okay, you have a root locus coming from this angle. Okay, so the intersection point is the point that is the phase margin you're talking about. Okay, if a root locus comes from here, okay, if a root locus is like that, right, your phase margin, the intersection, or whatever lah, okay, so you just need to look out for the intersection point. So let's say you have a graph over here, and you have a root locus like that, and then this is the radius 1, right? This intersection point will tell you that this is the phase margin that you're going to talk about it. So you just draw a straight line from the intersection point to the origin, and then you just find the phase margin from there. Otherwise, what you can do is actually find if you are given some delay, you can actually take frequency times delay, and then you get because frequency is radian per second, right? Times delay is actually second, so you have a radian. So when you change the radian to degree, you have your phase angle. Okay, you can actually find it from this video at delay. Okay, so this is a very normal concept. It's a trick question, okay. And then you make sure you can reduce. And then these are the criteria you need to know: 40 to 60 degrees phase margin, if you still remember. So if let's say you are given this thing, this is 40, this is negative side, okay, this is the positive side. So each 40 degrees phase margin, these are all the stuff that you're not allowed to be in. Other than that, you're safe. Okay, in this green zone, your locus is safe. Okay, so this is what it's all about. And then remember all the Nyquist stability theorem definition, all the definitions, what are the gain margin, phase margin, what are the criteria, okay, stability criteria, what are we looking for? We're actually not looking for the right half plane 0, because in our course we didn't plot any any zeros or poles in the right half plane, right? Imagine this is the thing, and then if you want to plot the poles and zeros, right? We didn't plot over here, typically we will always plot over here. That's all. So this is why it reduces to just saying that not encircling the critical minus 1 point will do, or touching the minus 1 point will do. Because if you encircle the minus 1 point, okay, let's say this is the minus 1 point, if your root locus encircle this 1 point, you are unstable already. Okay, this is what it says lah. And then you have to remember all these things. You just read it up lah. Remember all the criteria, understand all the definitions and such. And then another thing I want to know is that the intersection point of imaginary and real axis is a little different. Make sure you go. Okay, just a quick touch up, and then we can call it a day. Okay, so if you want to find real axis, right, you go negative 180 degrees, then it goes to tangent negative whatever transfer function that you have lah. Okay, and then you compare, and then you derive using trigo and complex number. If it's in imaginary axis, you can actually use negative 90 degrees, and you can actually solve for it. So this is actually, so the negative 90 degrees and the negative 100 degrees is the concept on the trigo rule. If you're talking about the complex rule, it's just simply saying when imaginary equals to 0, or when real is equals to 0, right? So at this point, imaginary is equals to 0, right? As you can see, this imaginary is 0, and at this point minus 90 degrees, the real axis is at 0. So this is the concepts I want you to know, and all the trends of how the Nyquist plot integrator and such. So I'll see you in the next lesson. Okay, now Nyquist plot has ended, so hopefully it will be more easier. I'll see you in the next video for next lesson for other things. So good luck!